So let's just recall where we are very quickly. we and we're in the virtual classes, right? uh, we we were sort of at the point where we could say, okay, so now we experts in the Hamiltonian formalism, and of course, at that stage, of course, everyone, every normal brain starts searching for some shortcuts, for some simplifications, right? What can be done in order to make your life in the world of research easier, right? From the point of view of physics and mathematics, right? From any points of view, right? And of course, what can be done? There is only one way. You can go to a different set of coordinates instead of your sort of original. Usually, we start with Cartesian, right? Instead of using your original set of okay, I usually words coordinates. It's better to use the word variables, right? Instead of original variables, you can go to different variables in an attempt to make your life easier, right? But the thing is, when you in the Hamiltonian formalism, if you go to a different set of variables, no one can guarantee that your final destination, in the final destination, you still can use Hamilton's equations. It's not like in the Lagrangian formalism. It doesn't matter where you go, the form of the Lagrange equations is going to be preserved. But in the world of Hamiltonian formalism, it's different, right? Hamilton's equations, so you have to be careful. If you go to somewhere, Hamilton's equations might not work, right? So it means that what? It means that we need to develop a set of, I don't know, we need to develop a procedure. So if you follow that procedure, and if you follow that procedure, when you go to a different world, then you will end up in a nice place where Hamilton's equations still correct and you can still use them, right? And you remember how we defined canonical coordinates. Canonical coordinates, it's a set of coordinates where Hamilton's equations are correct, right? So basically, we started developing this procedure. We just basically wanted to get some equations. If you satisfy those equations, it means that you will go to from one set of canonical coordinates to a different set of canonical coordinates. So it means that you will execute canonical transformation, right? So pretty much the whole chapter is all about that. How can we go from one nice place where a set of Hamilton's equations are correct to a different world of different variables where Hamilton's equations are still correct, right? So that's where we are. And so usually Q small, P small, we use to denote old coordinates. Okay, old variables, right? And Q capital, P capital, new variables. And of course, here there will be some transformation equations, right? Which are supposed to give us canonical transformation. So then, of course, we looked from the fundamental principle, right? We looked at variation of action in this set of variables and that set of variables, and by comparing them we ended up with this equation. So we must satisfy this equation, and when we compared those variations, we introduced a generating function f. We introduced the generating function f, which is called generating, and which effectively works as a bridge between the old variables and new variables, right? And we also showed that this function f should have 2n plus 1 independent variables. One, it's a time, so, and then 2n, what's left. And again, as I said, since it works as a bridge, so it makes sense to take 50% of coordinates from the old world and 50% of coordinates from the new world. As a result, we managed to create generating functions of 4 types. In first, 50% of coordinates from the old world, Q small, 50% from the new world, Q capital, generating function of the first type. And then similar, so second type, Q small, P capital, so we just replace Q capital with P capital. Then third one, P small, Q capital in time. and the fourth one, P small, P capital, and time. Again, the difference between small and P capital, there is a bar underneath. So if there is no bar, it means it's a small p. Right? Okay, basically, no, we also derived the equations. So first we started looking at function f1. Okay, so let me put a bullet, right? And first we'll look at function f1, which is function of q small, q capital, and t, and we derive the equation. So let me rewrite them. Okay, probably I will write in the column. So pi equals to partial derivative of f1. Okay, let me write dependencies. So it depends on q, small q capital, and time. And then with respect to, every time you differentiate with respect to the variable which is linearly independent. So in this case, q small, there must be q small. So that's why it's reasonably easy to remember equations every time you differentiate that function with respect to the independent variable. And here there must be canonically conjugate quantity to this one. So if we have here q small, there should be p small. If you have p small here, there must be q small there. If you have q capital, p capital must be there. So every time canonically conjugate quantities must be involved. Right. So that's equation number one. Then second equation. So in the second equation, there will be minus. I told you it's difficult sometimes to remember where pluses were the minuses, but here it's a minus. Partial derivative of f1 with respect to now independent variable q capital, right? And here we must have canonically conjugate quantity, so it must be p capital, right? So these are equations which we have to satisfy in order to get canonical transformations. And of course, the last equation relates Hamiltonians. Hamiltonian in the old and Hamiltonian in the new world. Right, so the last one, of course, no, I think K, yeah. Yeah, let me write K. K, Hamiltonian, which is, of course, should be a function of capitals H plus partial derivative of f1 with respect to time. And sort of jumping ahead, I can tell that Hamiltonians are related through the same equation. It doesn't matter which generating function you use, f1, f2, f3, f4, these will have exactly the same form all the time. Of course, these equations are going to be different, right? Okay, so if you have function f1, plug it here, and from here you're supposed to get transformation equations. So let's just show how we can get transformation equations from here. Transformation equations, look, the first equation, we have here p small, here we have q small and q capital. So after differentiating, we can invert this equation and write down q capital in terms of q small, p small. Immediately we can get the transformation equation. So from here we can get, here let me emphasize, so we solve it basically for this. And as a result, we'll get the first transformation equation, q capital equals to, will be a function of q small, p small, and time. Transformation equation of first transformation equation, which of course will give us a canonical transformations. Now, what about the second one? So now we need to get p capital in terms of q small, p small. In order to get that, we need to take this, plug it into the second. This brings q small, p small. Here there is also q small. So immediately we're getting p capital in terms of q small and p small. So the second transformation equation. So you will get from here p capital equals to p. Is a function of q, p, and t. Right? So transformation equations. So transformation equations. So that's how you can get transformation equations if generating function is given. But you remember I told you in the previous class, it's not, the situation is not as simple, because it's I told you it's sort of like a vicious circle. In order to get transformation equations, you need to get somehow a generating function, but there is no any particular rules which can be used, or procedure which can be used to get that generating function. Or you can get, we will see like in maybe in 10 minutes, how we can get generating function out of the transformation equations. But again, the same story. How can you get transformation equations in order to get generating function? It's a vicious circle, right? I told you, right? You can, I know, you can pray, meditate, think, right? How you can get either generating function or transformation equations. Okay, then the next step, of course, now, of course, after getting transformation equations, you need to rewrite your Hamiltonian or Hamiltonian, right? To get the Hamiltonian, right? And you know what? Of course, I can say you can just invert them and write Q small in terms of Q capital, or we can do it like this, right? Right. If you look at the second equation, we have here only Q small. Of course, if after differentiating, if you invert it, you can get Q small in terms of Q capital and P capital, right? Or sort of a reverse situation, reverse. Right. So from here we can get. Right. So let me probably show it even. I can move. Right. So from here, if you invert it, you will get Q as a function of Q capital, P capital, and time. So that will be the transformation equation in the opposite direction. Right. Or like books sometimes say, just out of this equation you can invert them and you can get how to go back. But you can also get from here. Then after this, how can you get P small? You will get this Q small, plug it here, right? And as a result, you will get P small in terms of Q capital and P capital, right? So as a result, you will be able to get P small as a function of Q capital, P capital, and time, right? So that's the transformation equations to go back, right? And so now, what about the Hamiltonian? Okay, let me rewrite it. I just want to show explicitly dependencies, right? So H, of course, is a function originally of what? Q, P, okay, and time possible dependence, and time, and plus df1, which is a function of Q small, Q capital, and time. Okay, sorry for the mess. I should have written explicitly dependencies in the first place. All right, with respect to time. So now, in order to get the final form of the Hamiltonian, you just need to remove all q's, all small p's from this equation. So you will take this, okay, let me use green. So this q small goes over here, goes over there, and p small goes over there. As a result, you will get Hamiltonian in the final form. It's all mechanical manipulations. Okay, mechanical mathematical manipulations. Right? Mechanical, I mean basically doesn't require any significant amount of thinking. Invert equation, right? Get this in terms of that, plug it there. Just simple manipulations. So that's how you can get transformation equations and new Hamiltonian out of generating function. Now, what about the opposite situation? What if transformation equations are given, and how can we get generating function? Right. because similar situation we're going to see maybe like in half an hour when we get to a more or less realistic example, right? Okay, now which way I should label it? Okay, let me write that. How can we get F1 out of transformation equations? It's also possible. Oh, the question mark, right? Okay, again, it's all the time we have to dance around these equations, right? Actually, these equations, this just relates Hamiltonians. So, all right, in order to get function f1, we basically need to write p small in terms of q small, q capital, and then we should be able to integrate this. Then, next, okay, maybe let me write that down. So how can I get that? Actually, over here we already. No. First, let me write down. Okay, the beginning. So as I said, how can we get from the transformation equation? So of course, first we assume. Let's assume that we have transformation equations. Okay, first step. All right. So transformation equations. Q, P, and T, and then P capital. Function of Q, P, and T. Okay, so that's given. And so now, as I told you, now from here we need to get how P small depends on Q small and Q capital in order to insert into this equation for an integration. So where can we get that? From the first equation. You see we have P small, Q small, and Q capital. So if we invert this equation, if we can extract P small and write it in terms of Q small and Q capital, yeah, that's the first step, right? So let me write it down. So this is given, right? And now from the first equation, of course, we can write Pi will be a function of Q small, Q capital, and time. and then and put it into this equation, right? It will be Pi as a partial derivative of f1 with respect to qi, right? So you just plug it here and integrate it, right? So and then integrate. So, but then of course we still have the second equation. So with the second equation we have to do similar manipulation. So we need to write now P capital in terms of Q small and Q capital. So how can we get P capital? Here we have P capital. We need to get rid of this P small, right? So we can take this equation, plug it into that, and as a result we'll have P capital in terms of Q small and Q capital. So in the form which we need for the second equation, right? Okay, so now after this, of course, after plugging, we can get what we want. P as a function of Q small, Q capital, and time, and then put it in the second equation. That's one, right? Okay, here it's more difficult to write. Okay, let me try it. Okay. Minus partial derivative of f1 with respect to q capital, right? So as I said, yeah, now we just need to plug this into equation and again integrate it. And then, of course, this, what you get from this equation must be combined with that equation, right? So, of course, you'll have some constant of integration, which is a function of this variable, function of that variable, or just regular mathematical manipulations must be done in order to get function f1. We will, in the example, as I said, maybe like in 15 minutes, I will show how it can be done. Okay, so now if you combine result from this equation and from that equation, you should be able to get function f1, right? So you can get function f1, which is the function of q small, q capital, and t. Again, it's just a procedure. Reasonably straightforward, right? So that's how you can get transformation equations if generating function is given. That's how you can get a generating function, f1 of the first type, out of transformation equations. Okay, now one example, very, very simple example, but you will see why sometimes I like that example. No, not sometimes, why I like that example. So let me check if I mention everything. So h out of k out of h. Yeah, I should. Okay, cool. So now let's say somebody gave you a generating function. So let me write example. Example is very trivial, but again, as I said, in a few minutes you will see why it's worth of discussions. Right? Otherwise, I would skip it and never even mention. So let's assume somebody gave you let f1, of course, which is a function of q small and q capital, right, and time equals to. Time it's possible, but of course not necessary. So let's assume that generating function is a product of the old coordinate and a new coordinate. So that's the generating function. Somebody was generous enough to give you this generating function. So let's get transformation equations. Because basically it's the first, this procedure. Of course, in this case, it's trivial. Right? So we just need to drag this generating function through our equations. So it will be p I equals partial derivative of f1 with respect to qi, and of course it will be equal to qi capital, which is immediately quite an interesting result. Now the second, p capital. P capital equals to minus partial derivative of f1 with respect to qi, and of course it will be equal to negative qi. What is interesting about this? It looks like this transformation, of course, it will be a canonical transformation. These are, canonical transformation leading us from a nice place to a nice place where Hamilton's equations are correct. But look, during this transformation, it looks like we swap variables. Q small in the old world is a momentum, generalized momentum in the new world. Generalized momentum in the old world, basically now it's a coordinate in the new world. Okay, let me first state it right in words, and then we'll discuss it. Right. So basically, it swaps q which way? Q and P around. Okay, Q and P. All right. Of course, Q small, Q also I can write Q capital, P capital, right? It swaps them around. Of course, this example tells us that these variables, okay, that coordinates and momenta, generalized coordinates and generalized momenta, they are basically equivalent in the Hamiltonian formalism. And very often, because of that, they are called like canonically conjugate quantities. Canonically conjugate quantities. Okay, let me write that down. Right. So, okay, maybe I'll write here. So, Q and P. So, Q and P are equivalent in the Hamiltonian formalism. Right. And they are called, they oops, they are called canonically conjugate quantities. Canonically conjugate quantities. Okay, so that's okay, what usually books present. Look, but it's really interesting point. Shocking even, I would say. If coordinate now is momentum, or momentum is a coordinate. Now it means, look, it looks like that we're changing the quantities, right? Changing the nature, sort of, right? I'm getting immediately some ideas for if this is true in the nature. Again, they were trying to describe the nature, right? Immediately, I'm getting some crazy ideas like about a business plan. If we can change the nature of things, I can, for example, go to Poland, where there are lots of farms where they grow these plastic apples, right? Which you can buy in Hanafort or Market Basket, right? All right, and buy them there for cheap. Bring them here, call them oranges, and sell them for significantly larger amount of money. I can be rich. I can be a millionaire, right, with this business plan, right? It looks like that's what I'm getting. Okay, these are apples, these are oranges. And the profit is it goes to my pocket, right? So what's the problem with my business plan? The thing is, all right, during these transformations, quantities do not change their nature. And when we get to the examples, I will emphasize, I will show, right? It's still, if it's, for example, if in the original world, if this is a coordinate, I don't know, measured in meters, for example, right? It will be still a coordinate measured in meters over here. But the system, in this case, Hamiltonian formalism, the system treats it as a momentum. So it's still the same quantity, it's still a coordinate, but the system is going to treat it as if it was a momentum, right? It's sort of like again, if we compare with my business plan, right? Still trying to save my business plan, still wants to be rich, right? It means that if I bring here to the United States my apples, right? Those plastic apples from Poland, and if I can convince everyone here, this system, right, that my apples are oranges, yeah, then I can sell it for that price, right? It's sort of like in art, right? You know that famous painting by Malevich black square, right? For me, by nature, that painting black square, it's just a piece of black BS, right? But the whole world of art is convinced that this is the masterpiece, this is the work of genius or whatever, right? Because the system agrees, okay, we're going to look at this black square as the masterpiece, right? The system agrees to treat it as art, right? The same here. If I, let's say I have all media, I control all the media in the country and I convince everyone that, okay, apples now oranges, buy for double price. If the system agrees on that, yeah, then of course I will be a richer and I will be, all right, famous apple seller as oranges, right? Okay, so and that's what happens here. When you make these transformations, when you go to the new world, it's still by nature, it's still the same. We cannot change the nature of things. Apples are not oranges, right? So it will be still an apple, unless you convince everyone, right? Brainwash everyone, right? So if that's what this is a coordinate, over here it will be basically still the same coordinate, but the system, because again, what is Hamiltonian formalism? It's some kind of system model, right? How we treat things. If the system and yeah, there the system, the Hamiltonian formalism just treats it, use the equations proper, treats it as if it was momentum, right? But nature still the same, right? Okay, so I found that interesting, right? So to emphasize, otherwise it will be quite a banal example. I would just skip it and it's not worth of discussions, right? But it's very important that if we go somewhere, we don't change the nature. We're not gods to change the nature of things, right? Not yet, at least, right? Right. Again, at least you convince everyone in the world that you are God, right? And the system will treat you as a God. Okay, cool. All right, so now after this, enough about this function f1. And now let's play with the function f2. We're not going to play with f3 and f4 because, again, the procedure will be the same, slightly different, right? And just because different variables will be treated as independent. So, right. Yeah, and if we compare again with this terminology, now canonically conjugate quantities. So if that's, then instead of using names apples and oranges for those fruits, we can call them canonically conjugate fruits, for example, right? So nice name, right? All right, okay, back to F2. So that was F1. Now F2, you know what, let me compare here apples and oranges so that you will remember apples and oranges. Right, okay, now new bullet. What about function f2, which is the function of, should be a function of q small, p capital, and t. Generating function of the second type. So how can we get this function? How can we bring this function into the game, right? And I will show that we can get that from function f1. All these actually generating functions are connected, right? And connected again through that Legendre transformation, because what effectively the difference between them? Here, instead of this variable q capital, we need to introduce b capital. My neighbors are doing something, fixing something, right? So if you hear some noises, right? All right. So Legendre transformation can do that. And the same between, for example, this function and that function. You just need to remove q small, introduce p capital. We know how that can be done using Legendre transformations. But now we're going to derive those results, that Legendre transformation. We're going to get it naturally, right? Okay. So this is the equation which we got, right, in the first place. And let me rewrite it over there and emphasize. You remember when we got that and we decided to use function f1, this equation fit perfectly. We didn't have to do anything. So effectively, this is function f1. This is function of 1. So we just expanded this row, this explicitly, and compared proper terms, right? Because everything this q small, q capital are independent, right? So this equation was perfect for f1. But what about if we think about using f2? Okay, let me rewrite that equation one more time here. Right, so pi qi dot minus Hamiltonian equals to p. Okay, it doesn't look, it looks like d, not p. Right, p q dot minus Hamiltonian and plus, and now I will write f1 over dt. So that equation fit perfectly for f1. So we didn't have to do anything with that equation. But now let's look at each term in order to understand which terms are wrong or will be wrong if we do decide to use function f2, which is a function of q small, p capital, and t. Right. Again, you can multiply, for example, the whole equation by dt in order to make it even more convenient, right? If you multiply it by dt, you will have here p dq, here h dt, p dq, k dt, and df. And look, in this function, q is independent, and we have differential of independent. Good. It's a good term, right? It will allow us to extract an equation which we will need, because we will have to compare terms connected to linearly independent variables, right? Then h dt, also good. Then p dq capital. Q capital is not our independent variable. This term ruins everything. It will not allow us to get an equation. So we need to get rid of this term and replace it with p capital, so that we will have here dp capital or p capital dot, right? So this is a wrong term. Wrong one because of q capital, right? And again, replace it with p capital. It will be very simple. We'll see. Then here, k dt will be also good, right? Because t is independent. And here we will see what can be done. Because yeah, I will show you how we can fix that. Okay, so now let's fix this term. And of course, we can easily replace it. If you look at the total time derivative of the product, every time I write something strange. P capital, Q capital, total time derivative of this product. Of course, you will end up with Pi dot Qi and plus Qi dot Pi, right? So we need to get this term, right, and replace, right? So over here we'll have this term minus that term. Okay, let me rewrite it. So we will get d over dt p capital Q capital, right? Then minus this p. You know what? Let me write first Q. It's not a big deal, but still makes me feel better. Qi pi dot, right? It's this term, and then minus k, and plus this, plus total time derivative of f1 with respect to time. Obviously, these two must be combined. All right. All right, and you know what? Let me separate this. And I will combine those terms. Oh no, I think I forgot something. Oh no. I have a strong feeling that something is missing. No, it looks like everything is good. Everything is good. No. Sometimes I have these doubts. So it will be minus q p dot minus k and plus d over dt out of f1 plus p I q I. Right. Okay, so now I claim that this is my function f2, which is a function of q small p capital, right? So I claim, and of course I will prove it. So f2, which is a function of q small p capital and t, so that f1, which is a function of q small q capital and t, plus p q. That's how I introduce function f2. Okay, I will frame because I know it's correct. Right. And it shouldn't be a surprise. Look, because I already mentioned it several times. It's all about Legendre transformations. Look, what is effectively difference again between function f1 and f2? That instead of a q capital variable, we have p capital variable. And we know how we can replace a single variable in the function. Legendre transformation. You take the old variable which you want to remove, multiply it by the new variable which you want to introduce, and add or subtract, it depends, right, from the old function. It's a Legendre transformation, one of the form of that Legendre transformation. But still, it shouldn't be enough. I still need to convince you, I still need to prove that this function, which is constructed like this, is not a function of p small and q capital, right? Sort of excluding, right? So let's show that what I constructed is not a function of p small and q capital. How can I do that? How can I convince? Let me differentiate. Let me take a partial derivative of what I introduced. Take a partial derivative with respect to p small and q capital. If those derivatives are zeros, okay, it's a proof, right? As a result, will be what's left, q small and p capital. Okay, so let me write something. So is f2, the way we introduce it, is f2 indeed independent of q capital and p small. All right, q capital and p small. Okay. Again, you see, we're excluding, right? So if it's not a function of those, it means that it should be a function of q small and p capital. So let's look at the partial derivatives. If those derivatives are zero, of course, that's the proof. So let's look partial derivative of f2, okay, the way we introduce it, with respect to, let's start with p capital. Okay, so partial derivative of f1. So df1 with respect to pi, and partial derivative of that, again, it's a partial derivative. It only search for explicit presence of a variable, right? So explicit presence of p capital is there. So of course I will get plus q. Hold it. No. Q capital, right? I said indeed of. So I have to differentiate with respect to q capital, right? Right. I said one thing and started writing the other one, right? So, and then when I started getting closer, all right, I started realizing that something is, all right, fishing. Okay, so of course here we'll have p capital, right? Okay, now it looks better. And so what is df1 with respect to q? Df1 with respect to q capital it's a minus P capital. So this is minus P capital, of course, sub I, minus P sub I. So minus P sub I plus P sub I, of course, you end up with 0. Okay, great. So it doesn't have dependence on Q capital. Now, what about P small, right? P small. So now let's look at the derivative with respect to that. So partial derivative of F2 with respect to Pi. Again, partial derivative, only search for explicit presence, right? With respect to P small, function F1 doesn't have P dependence. It depends only on Q small and Q capital. So F1 gives us a derivative of F1 with respect to P small gives us 0 immediately, right? And the second term also, there's no explicit presence of P small. Of course, plus partial derivative with respect to Pi out of P capital Q capital, of course, it's also a 0. Again, the same 0. So great, it works. That's exclamation sign mark, right? Okay, yes, it's that is a function only of Q small, P capital, and time, right? So that's how actually that's the relationship between P small and between F2 and F1, right? So if you know F1 function and if you don't like it, you can go to F2 function, right? Pretty much the same transformation you can get using pretty much any of these functions, right? You will see it in the examples, and in your homework there will be examples. So now back to this. So we introduced this function F2. So let's get an equation, right? Similar to this, but now of course equations for F2. So right now we basically go back to this, right? Let me show that. Basically go from there to here. We proved that it's a function of 2. And now let me rewrite this. So it will be Pi. You know what, probably I should have extended this line to over here, right? Wrong color. Right. So that line, I'm continuing here. So Pi Qi dot minus H Hamiltonian, and then this minus Qi capital Pi dot P capital dot minus Hamiltonian, and then of course now it's a function of 2, and now let me write explicitly, because yeah, function of 2, it's a function of Q small, P small, P capital and T, and we need to differentiate it with respect to time. So I can write immediately, start writing. So plus partial derivative of F2 with respect to time. So first I took care of time, right? Then plus partial derivative of F2 with respect to Q small and Q small dot, and then P capital. Now the second one, plus partial derivative of F2 with respect to P capital and P capital dot. Yeah. Okay, so now look, all the terms are correct terms. Q small, independent. Of course here, okay, dq, again, as I said, you can multiply the whole thing by dt to make it look even better. So you will have here dq, good, dt, good, dp capital, good, because p is independent. dt, again, here you'll have dt, here dq small, which is good, and again, dp capital, good. Again, all terms are the correct terms, right? because we want to have only terms where we have differentials of linearly independent variables. And now it's perfect. But here, these terms was messing up with the beauty of that expression. Right. Okay, so now we can say, of course, in simple words, just by comparing terms, we should be able to get the equation. But of course, no, we need to compare terms where we have linearly independent differentials of linearly independent variables. So it means what? P small and that this with this, then this guy with that guy must be equal, right? They must all cancel each other, and then the rest. Right. So we're getting the equations which we need in order to get transformation equations out of generating function f2. Okay, so the first one. All right, so pi equals pi equals to, they're on different sides of the equation, so it will be partial derivative of f2 with respect to, just a second. Okay, this term, why I'm staring at that one. Sorry, everything is good. So this and this. Okay, so qi, awesome. No. Then this with that, again, you see this term and that term on the same side of the equation, so we'll get that this q capital, qi must be equal to partial derivative of f2 with respect to pi without minus. Right. And so then, of course, equation relating Hamiltonians. Okay, let me try to squeeze it. So k in the new coordinates equals to h in the old plus partial derivative of f2 with respect to time. And as I told you over here, this equation exactly the same. It doesn't matter which generating function you use. Equation relating Hamiltonians exactly the same. It doesn't matter which function. All right. So now let's again outline quickly how can we get transformation equations out of this. Right. And in order to do that, let me show explicitly dependencies. Right. So f2 depends on q small p capital T, and here also let me write. Right. And so p capital, after differentiating, we can get p capital, and we can write it in terms of q small, p small. First transformation equation. So from here, we can get the first transformation equation. So it will be p equals a function of q small, p small, and time. So that's how we can get the new generalized momentum. And then if we take that, plug it into the second equation instead of p, we will be able to get q capital as a function of q small and p small. So as a result, we'll get q capital as a function of q small, p small, and time. Yeah, transformation equations. You know, probably I should have framed these equations, right? Yeah, because, and again, you see, it's easy to remember every time you differentiate with respect to a linearly independent variable. And over here, you must have canonically conjugate quantity, right? Canonically conjugate quantity. Right? And here the same. Again, you differentiate with a linearly independent, right? And canonically conjugate over there. Pluses and minuses. F function f2, I just remember, it's a nice, it works with pluses. Here you have plus and there plus. Function f1 in the second equation you have minus. All right, and of course, yeah, you can then you can get what q small p small. I use them here in order to get Hamiltonian in the right form in terms of the right variables, right? So again, it's just mechanical transformations basically, right? Yeah, that's it. We're not going to discuss, as I said, function f3 and f4 because effectively you'll have to repeat the same steps over again, right? So you will have here still function f1 and you will look at this equation in the search for a wrong terms or for wrong terms. And again, you will try to replace them using what's similar, right? And then total time derivatives you combine with function f1. As a result, naturally, you will get similarly function f3 and function f4, right? And again, the same procedure, you will end up with the differential equations, which can give us transformation equations, canonical transformation equations, which guarantees that we will end up in a new set of canonical coordinates. Right. Okay, but as I said, we in this semester we're going to use only function f1 and f2, f3 and f4. No. Okay, so now let me just write down all these equations for all generating functions, right? And then we will start looking at the example. Most likely the example will be next class. And I told you in the previous class that you will see how much of efforts I will have to apply in order to get generating function, because there is no nice procedure, right, or algorithm which can be used to find the generating function. Or every time you have to somehow fudge it, either or transformation equations you have to fudge it somehow, or generating function. It's all every time it's sort of like a mixture of art with voodoo and physics. All right, yeah. So let's just summarize. So function f1. Okay, probably I'll grab my notes. So f1, it's a function of q small, q capital, and time, right? And the transformation equations we can get from these equations. So the first one, p, did I use I? Yeah, let me use subscripts. Partial derivative of f1 with respect to qi, right? Then probably I will write in a line. Then the next one, of course, p capital minus partial derivative of f1 with respect to qi. Okay, over there I will write how these generating functions are related to each other. But first function f1, it's sort of like a reference point, right, which is not related to anyone or anything. But then function f2, of course, will be related to f1 and so on, right? And equations are relating Hamiltonians exactly the same. Okay, maybe I will write it underneath. I will write it underneath of everything. So now function f2. f2, which is the function of q small, p capital, and time, and now transformation equations. So it will be first pi equals to partial derivative of f2 with respect to qi. And then now it should be q capital equals partial derivative of f2 with respect to pi. And equation relating generating functions, which we just derived naturally. But again, it's just a Legendre transformation. So I can rewrite, so f2 equals f1 plus the old variable which you want to remove times the new variable which you want to introduce into the function. So that's the relation between them, right? So now f3. So f3, which should be a function of p small, q capital, and time, right? And the transformation equations, again, I can write them down, but signs, I don't remember signs, right? So, right, so it will be q small equals to partial derivative of f3 with respect to this linearly independent. Sign, I don't remember, I need to look, minus, here actually minus. Right, then p capital equals partial derivative of f3 with respect to this qi, and again the sign, again minus. And the transformation, I mean the equation connecting f3 with f1. f3 equals f1. And again, look, what's the difference between f1 and f3 in terms of variables? We need to get rid of q small and introduce p small. So here we must have q I pi product, right? And the sign is plus. Oh, just a second. No, f minus, right? Okay, again, so old, new, right? And the last one, f4, which should be a function of p small, p capital, and time. So now, again, transformation equations can be obtained from here. So q equals partial derivative of 4 with respect to this pi, and the sign, I will look my notes, minus. Second equation giving us transformation equations. So here it should be qi equals to partial derivative of f4 with respect to linearly independent variable pi, sign plus. And now, again, if we try to relate f1 with f4, there will be not just one term, but look, we need to get rid of q small, introduce p small, it's one term, and we need to get rid of q capital, introduce p capital, second term. So as a result, I can write that f4 equals to f1, but again, pluses and minuses every time I have to check my notes, right? So, as I said, to get rid of this q small, p small, and with minus, and get rid of this, introduce this, we must have q capital, p capital, sign. Wait, just a second. There, this is minus, and then plus. Plus q capital, p capital. Again, Legendre transformations. Every time, in order to move from the Lagrangian to the Hamiltonian, effectively we use Legendre transformations. Now, if you want to hop between these generating functions, again, just Legendre transformations all the time. And equation connecting Hamiltonians. So Hamiltonian equals to Hamiltonian plus partial derivative of f. 1, 2, 3, 4. It doesn't matter which generating function you want to use. Partial derivative with respect to time. So that's the whole scope. And again, very often, the same problem can be easily solved using function f1 or f2, right? In your homework, I will give you problems where you have to just first apply function f1, then go to the function f2, and of course you will end up with the same results at the end. Another thing which I wanted to mention. Look, basically time is not in none of these equations, right? These transformation equations. Time is not involved. It means what? It means that if your generating function is time independent, okay, it doesn't have explicit time dependence, then you can tell immediately that your transformation equations, when you get out of this, right, which you can get out of these, will be also time independent. So you're not going to see explicit time dependence, right? We will use that from time to time. And of course, the reverse is correct. If your transformation equations do not have explicit time dependence, your generating function must be also free from time, right? And yeah, and of course, every time, don't forget to remove all wrong variables in this equation, right? So all the q small p small must be replaced with q capital P capital. And of course, it all comes from the transformation equations, right? Actually, I showed it over here. I erased it. So now, example. That's the fun part. All right, I will just probably state the problem, and we will continue next class, right? So, example, harmonic oscillator. And we already solved this problem using a couple of methods. And you will see that we are going to solve this example using all possible tools, all possible classical mechanical methods, right? So, example, harmonic. Example. Of course, harmonic oscillator. Right. The simplest possible. Some kind of one-dimensional. Of course, it can be simpler than just a mass spring system. But why not? I can draw just the simplest. All right. So we have a spring, mass, right? M, spring constant K. Of course, let's say this is right equilibrium, and of course, position of that mass can be described by the generalized coordinate q, right? And so let me write Lagrangian Hamiltonian, and from there we will pick up next class. Of course, we can write the Lagrangian. It will be m over 2 q dot squared minus v, which is 1 over 2 k q squared. And of course, you can easily make a transition to the Hamiltonian, right? Now you're an expert, you know the procedure. So of course, you will end up with the Hamiltonian, which will be p squared over 2m and plus 1 over 2 k q squared. So that's the Hamiltonian. Let me introduce immediately the constant omega squared sk over m, right? And of course, this can be rewritten as 1 over 2m p squared plus m squared omega squared q squared. Okay, you know what, that introduced constant is in my way. Okay, let's introduce it here. Omega squared equals k over m, right? Okay, so that will be our Hamiltonian, right? And from this point, we will continue next class. So pretty much at the most interesting part, because you will see how much of funky moves, finicky moves I'll have to make in order to solve this problem. It will be really funny. Every time doing what we want, what can be, how it can be achieved, how we can twist it, construct this or that. It's again, I like the method. It's very elegant, but at the same time, in order to get into this method, in order to get transformation, in order to get generating function, it can be really tricky. Otherwise, it's a beautiful method.